Today, I'm going to give you a quick introduction to bitwise operators. Bitwise operators are very useful in embedded development because they allow us to operate the variables, the variable values at a bitwise level. We can change bit by bit the variable, and this is very useful in embedded devices because sometimes we just want to, for example, in the case of an output, maybe we just want to set a specific output. We want to turn on the specific output, or we want to turn it off. Also, in the registers, we might want to enable one bit in the register of the microcontroller, or we might want to disable the bit. We can do this using bitwise operators. Let us start with an example. I'm going to delete this. I'm going to start with a simple 8-bit variable. Okay, actually I'm going to declare two 8-bit variables, and I'm going to declare here a 1 and b 1. Okay, let's do one more. Wind 8 c is going to be equal a and b. Let's do the AND operator. Let's do the AND operator, and let's see what we get from this operation. Build the project. Let's flash it into memory. Now let's do a step by step. Okay. One, A equals 1, B equals 1, and C should be 1 and 1. That should be 1. That is the operation of 1 and 1. Now what happens if we do let's do here we're going to do C A XOR B, or perhaps we want to do C equals negated A. Let's try these ones out. Or perhaps A or B. Let's build. One C equals 1 equals 0, and C negated A equals 254. A or B equals 1. Now let's see, to have a better understanding, let's see if we can change this to number format, a binary. Yeah, let's change it to a binary. We can appreciate better if we Okay, number format binary, okay, and let's restart this right here. Go reset. Alright, now this is restart. Yes, restart. So let's restart the process again. Let's do here A and B. You see the first bit, only the least significant bit is 1, and if we do a AND operation, 1 and 1 equals 1. If we do an XOR, 1 XOR 1 equals 0. And if we negate, what's going to happen here is all the zeros are going to be inverted to ones, and all the ones to 0. Here, C equals negative value of 1. This one was negated, so it's 0, and all these zeros were negated, they became 1s. Let's do the OR. 1 or 1 equals 1. This is how we can do bit operators. So now let's do the following. We're gonna do A equals, we're gonna use this shift. These are called shifts. Why? Because we're gonna do now let's do 1. We're gonna shift it. We're gonna shift the value 1 by 1, and then we're gonna repeat this operation A and B. Let's shift it by 2 values. Okay, let's see what happens. We build flash. Okay, we step into this. So now we're gonna do A equals 1 shifted by 2. You see here, 1 shifted by 2 would be, if it's not shifted, 1 would be like in this case, the least significant bit. If it's shifted by 1, then this would be 1. If shifted by 2, then this becomes 1. So basically the 1 is being shifted as many times as we indicate. In this case, we're indicating twice. Please shift this 1 twice to the left, and that's exactly what's happening. So what will happen if we do A and B? 1 and 0, 0, 0 and 0, 0, 0 and 1, 0. We're gonna get zeros in Z. See, all zeros. Why? Because when we do 1 and 0, we get a 0, 0, 0, 0. If we were doing an OR, like in this case, then this would be 1 and 0, 1, 0 or 0, 0, 0 or 1, 1. Let's actually do a OR. Let's do a OR, and let's do an XOR. Alright, and let's also do unnegated. Okay, let's do a shift. I'm gonna shift now we're gonna do b equals 1 shifted by to the right. I'm gonna shift it 2 places to the right. Okay, let's do same operations. Okay, let's try this out. We start with ones. Okay, we do basic operations. Now let's shift 1 2 places. Let's do an AND. We already know that 0 and 1 equals 0. 0 and 0 0, 1 and 0 0. Okay, so now let's do an OR. 0 or 0, 0 or 1 equals 1. 0 or 0 equals 0. 1 or 0 equals 1. This is the result of the operation. Now let's do an XOR. What is the result of the XOR? 0 XOR 1 equals 1. 0 XOR 0 equals 0. 1 XOR 0 equals 1. Now let's do a negative. Let's negate 8. Here, all the zeros get converted to 1, and all the ones get converted to 0. That's basically what's happening with this operation. We are negating. Give me the opposite of the bits contained in A. These are exactly the opposites of the bits contained in A. Now let's do B shifted twice. Oh, we'll get a 0. Yeah, we're gonna get a 0 because we're shifting to the right. So let's do A and B. We're gonna get all zeros because B is all zeros, then C becomes zeros as well. Let's do an OR. You see all zeros except for the one where A has ones. 1 or 0 equals 1. All the rest are zeros. You do an XOR. We get the same result. They are negated. You get exactly the opposite of A. So these are the basic operations that we have for our variables. If we want to manipulate at the bit level, we can use any of these, and we are going to be using these operators when we want to manipulate the value of our registers. We're going to talk about pointers. Pointers are a very useful feature in the C language, and they are also very useful in embedded development. Now we're going to see how we can declare, how we can use a pointer. We already know how to declare a variable. We can declare a variable like this. We specify the data type, name of the variable, the value of the variable. Now, to declare a pointer, what we have to do is specify the data type, and we use this naming convention. We use the asterisk, the name of the pointer, and equals. We use the ampersand. What we are basically saying here is declare a pointer of type integer and point this to the address of A. The ampersand basically indicates, is telling the compiler we want the address of this variable. Wherever it is stored, we want that the value of that memory address here in this pointer. And We can also modify, for example, I can modify the value of the variable, or I can even modify the value of the pointer. Let's build this and let's flash it. Okay, now I'm going to monitor the variables. I'm going to do step by step. First, let's initialize A. I'm going to change this to something more comprehensible, decimal. Same thing here, decimal. Okay, now let's initialize the pointer. Okay, so here, as you can see, the value of A equals 3, and it is stored in this address right here. So if we go to the address, no, sorry, okay, here you go. If we look at the address 1FA, we see 3 is stored here. Okay, when we initialize the pointer basically here contains it's contains, let me put this in an hexadecimal so we have better x. Yeah, okay, the pointer contains the value of the address. The value of the address is this 2000 something 1F8. That's the value of the pointer. And when with the reference, this is called dereference the pointer. With the reference the pointer, it will give us the value of this address, that is 3. It's giving us basically 3. So let's see what happens if I modify the value of A. The value of A gets modified, and so does the referencing of the pointer. Now the pointer is telling us what is in this memory address. It's a 5. We have a 5. Let's see if Code Composer updates here. Yeah, it is. See, the value is updated to 5. We can also update the value of directly the value of the memory address by modifying the pointer. Let's update it with 7. See, we updated the reference of the pointer to 7. Also the variable got updated to 7. And let's check the memory. Well, the memory is still 5. Yeah, for some reason Code Composer here is not updating this, but here we can see that the value of the variable has been updated to 7. Let me see if a refresh can do it. Yeah, there you go. I saw it. Yeah, now the value is 7. We did this by updating the pointer. We can manipulate the memory address, directly the memory address, changing the value, and therefore the variable which is stored in that address will get modified as well. This is one of the very useful things that C language offers. This is very useful because we're going to see later when we want to modify a register, like the let's say peripherals. We want to modify a port to set an LED, or we want to read some switch that we have connected in one of our inputs. We can read directly and we can modify directly the memory address of that register. By doing so, we are manipulating the peripheral of our the peripherals of our microcontrollers. Now that we know how pointer works, here here I have graphical representation of what is a pointer. Here we can see that we have a variable called bar with a value 10, and this variable is stored in this address in green. It's 7FFFA00, all this. That is the address in which this variable is stored. When we declare a pointer, the pointer PTR basically contains the address in green, contains the address of that variable. So every time we use it, every time we dereference the pointer, it will read whatever is in the memory. In this case, a 10. We have a 10 stored in the memory, and that is exactly what we are going to get every time we read the pointer. Now, let's see how we can use pointers to, let's say, to modify a register. In order to do that, what we have to do is I'm going to define sys tcl ctl, and what I'm going to do here is I'm going to grab the address. This is a register in the microcontroller that is used to configure the like the clock of the microcontroller, and this is its address. This is where the register is located. If I want to configure this, what I need to do is I need to declare this. First, I need to give it a data type, volatile win32. I'm going to use this, and then pointer. Here basically I'm telling it this is going to be a type volatile, 32 bits long, and it's going to be a pointer to this address. And then I want to make this a pointer and now I can manipulate this this register by assigning it any like this, any value that is 32 bits long. It has to be 32 bits long. I can manipulate it like this. By doing this, I am basically configuring the register for the microcontroller. The Stellaris microcontroller, the Tiva-C that we are using, has basically, here we can see a port control and a mode control. These two registers have to be configured. We have to configure those in order to start using the inputs and outputs that the microcontroller has available. And we have more registers, as you can see, but right now we're going to focus only on these two. We're gonna do a blink application. We're going to turn on and turn off one LED. This is a diagram of the launchpad, the one that we're using for this exercise. This launchpad has already 3 LEDs connected. We can use those 3 LEDs And those three LEDs, as you can see in the diagram, we have LED RGB. One is red, blue, and green. And these are connected in the port F. They are connected in pin 1, 2, and 3 of the port F. So what we have to do is we have to configure port F, bits 1, 2, 3 as output, and then we have to write a 1 or a 0 in those three outputs, and we can manipulate. We can actually turn on those LEDs or turn them off depending on what we write to the output. So we're gonna do that